Welcome to Xcoder Videos and to the last of our sessions on the Microhard program. We're going to be looking at the final task of the game, which is the CPU. And it may be perhaps the most difficult of the components to build, though not because of its complexity. I'll talk about a little bit one of the reasons why it was difficult when we get into it. But I do want to say that I mentioned in another video previously that I am planning to have a live video sessions on Friday night at 7 o'clock Central Time, where we will be continuing in a way the same thing that we're doing here, but not with the Microhard program. My plan is to use the digital application as a sandbox where I will present some specifications for various components, perhaps a little more complicated than what we find within Microhard, and maybe even a little more realistic than what we get in the Microhard program. And then a week later or a couple of weeks later, depending upon how difficult the tasks are, we'll present a solution for the components that I give previously. And I hope there'll be some enjoyment out of that, and perhaps we'll learn some things as well as we go through and look at these components. But that's going to start in a couple of weeks. Let me take a look at a calendar here and see if I can. Well, it won't let me look at the calendar that way. Let me do it this way. We'll come over here. Look at the calendar here. 2 weeks will be the 22nd of March. So Friday night, the 22nd of March at 7 p.m., we will start with our live video series. I hope that you'll be able to come in and watch those with everyone. As I mentioned, we are on the last of the tasks in Microhard, which is a CPU. And this CPU uses the components that we've built before, especially the decoder and the ALU that we've built, and integrates that into a logical system here for the CPU. The CPU has an instruction bus, 16 bits. This is used this is used to present the, oh, I don't know what that's used for. I'm having to think about this for a minute. We have the instruction address, which is 16 bits, and the data address, which is 16 bits. And we have a data input of 16 bits, and we have instructions of 16 bits. And this, I suppose, is coming from these instructions come from the address that's pointed to by the instruction address. Now, ordinarily, a CPU would just automatically pull the instruction up from the address that it has, and it doesn't need any help to get that. But we've got a kind of an interesting CPU here. The result is the output of the CPU, and The right bit is a bit that is equal to equal to one of the bits off of the decoder. I don't remember right offhand, but it instructs the computer to write the address or write the result into a specific address in where the data address is pointing to. And then the reset pin is a pin that sets everything to 0 and starts the CPU addressing the memory addresses from 0. There are basically, the way this is designed, it uses two different memory different memory segments, or two different memory components, one for the instructions and one for the data address. That's kind of odd for a computer. Normally the instructions and the data would be in the same memory, not at the same memory place, but it would be within the same memory of the computer, and you just have one giant set of memory, and then the computer, the CPU and the program would figure out where everything was supposed to be, so that there wasn't any conflict between that. But in this case, they separate the instruction from the data address. The instructions are very difficult. They were difficult for me to understand, and I had to kind of go in and rewrite the instructions so that I could be sure that I understood what the instructions were talking about. Primarily down here in the behavioral specification, that's where you get the information for how the CPU is supposed to work. One thing I found difficult in these instructions is that sometimes the instructions tell you where a result goes to, and in other sentences it tells you where the result comes from. And by mixing those up, it gets to be pretty confusing. So I went through and tried to normalize all this so that all of my to's and froms were from the same direction. And this is what I came up with in my efforts. I brought this up in Notepad, and you can see here in Notepad, it's the same instructions that were given in Microhard, but I took an instruction like this. If the CTM and load M output of the decoder is 1, the constant output has to be loaded into the MR. And I just simplified that and said CTM and load M, and basically that is a condition that CTM is true and load M is true. Then put the 15-bit constant into MR. And then if load M is 1 and CTM is 0, then the result of the ALU operation has to be loaded into the MR. So I put not CTM and load M, and ALU result into MR. And so I just did that for all of these instructions so that I got the source, or the condition, and then the result. Condition, result, condition, result. And that simplified things for me, made it easier for me to come up with a design. Then for the op2 conditions, the op2 was the second of the operands that the decoder could present. It's at 0, 0. Then the 5-bit constant goes to ALU N2. This is the second. This is going to be a multiplexer actually, but it's the second of the. Oh, wait a minute. That should be N1. Sorry. The first of the first 0, 0 points to the will point to the first uh, uh, input into the ALU, and then not to the ALU, but to this is actually going to be a multiplexer that goes into the ALU, and so 0, 1, the AR to the ALU N2, or to the multiplexer for ALU. This should be 3, and then 4 for those multiplexers. If it's 0, 1, then it goes into N2. If it's 1, 0, it goes into N3, 1, 1 into N4. And that was a little bit easier or simpler for me to understand than trying to read through this and understanding what it was just by looking at it. And I just couldn't do that. And then under the jump if Z, and if the ALU 0 is high, then we put the register, the M register value into the PCN. If ALU out will go to the result going out, MR out will go to the data address, and the PC out will go to the instruction address, and reset goes directly to the PC reset. And that's a simplification of the instructions that were given in the specifications for this component, but I thought it was a lot easier to understand once I did that. All right, so let's take a look at the design that I came up with. I had this up just a moment ago. And it really, for a CPU, it's not very complicated. I kind of had difficulty arranging things in a logical order and a logical place where I could keep everything in mind. I actually ended up doing this 2 times, so that the first time I really wasn't satisfied with it very much. My design was a lot more convoluted in the first one, even though it did exactly the same thing and the wires went almost to the same place in every case. It was just more difficult to see what was going on here. But let me point out some things. This is the decoder up here that we will use in the application. But it has an instruction input. The decoder has an instruction input, and the CPU has an instruction input, which is fed into the decoder, and then the decoder takes the instruction and composes the output for all of these pins. Some of these are buses, and some of them are just simple 1-wire pins. C to M means to load the, basically means load the M register, or the C to M, it means to load the constant to the M register. Load A means to load the A register. Load D is to load the, is to write the data. It's an output. It goes directly to the output of the CPU. Load M is to load the M register. Then there's op1, that's a single bit. Op2 is a 2-bit opcode or operand. Then there is an opcode that goes directly into the ALU, the jump if 0 flag to tells the PC to jump if the current operation resulted in a 0. The current operation in the ALU resulted in a 0. And so we have this logic here, jump if 0 logic. If 0 is high and the 0 bit of the ALU is high, then the load on the PC goes high, and that tells the PC, this program counter, to load up the value from the M register. Whatever the M register value is will get loaded into the program counter. And that's all of the decoder logic. This is the data logic. It's a 16-bit data input, and then a reset bit. If that goes high, then the PC just is reset. The program counter resets to 0, and we start back at 0. The rest of the logic here is to, for example, here, this and value is looking at C to M and load M. If both of those go high, then we send the output for this AND gate to these two components, the AND4 and the OR2. One of these is a 16-bit AND gate. This is a 1-bit OR gate. And so we had to convert the 1-bit to 16-bit in order to get it in there. That's not so difficult in Microhard. There's a little different way of doing it. But in this application, we use this little component to convert it from a 1-bit value to a 16-bit value. And so if the AND is 0, then the 16-bit value will be 0. And if the AND is 1, the 16-bit value will be all 1s. In this case, it'll be 15 bits because of, no, I'm sorry, it's a 16-bit. It's incorrect information. That is a 16-bit. So we do the same thing for this one. This one is based upon CTM being at 0 and load M being at 1. In that case, then the ALU result goes into the MR. So there's a little bit different application there. And these two things are ORed together here because we got the value from the 15-bit constant and the value from the ALU result. And one of these will be 0. The other one will be whatever the input value is. That will go through the OR bit to bring them together, and then to then into the M register here. And this goes high to load the M register, and this goes high whenever either one of these values goes to 1. And so that's the logic for the MR load. A L result in this logic is going to load the ALU, or the result of the ALU, to the AR. This is the A register down here. And so the ALU input is from the ALU, and this load A is a single bit, which we convert to 16. So we have 16 bits to AND with the ALU result. So that this will either be a 0 or whatever the ALU result is based upon the value of load A. And that goes on down to the A register. If load A is high, then the A register loads that value in. I have a little section here that I call a constant normalizer. And in this case, when the opcode 2 logic tells the program to load the ALU with the constant that is represented here on these lines, then the these values will be manipulated so that we have a 5-bit value. If the values are positive, then we're going to just send in the 4 lower bits, 1, 2, 3, and 4. And that's what this and logic does with the input of F and the constant up here. But if the value is negative, it's going to pad all the remaining bits with 1s. That's what the OR logic does here. It just pads all the remaining bits to 1. So we have the 4 lower bits, and will be whatever the 4 lower bits of the input would be, and then the rest of them would be 1s based upon the OR logic. And the way we determine which one of these values we use is by looking at pin 4. If you look at it from a zero-based pin numbering system, or pin 5, the way that they do it in Microhard, and this selects between these two outputs. And so if pin 4 is high, we're going to select the negative value and send it on to MUX 1. If the pin is low, if this pin is low, then we're going to send the positive value to MUX 1 into this area. MUX 1 determines which of 4 different values is loaded into ALU. And the various options are the 5-bit constant that we just spoke about, or the value from AREG, or the value from the MREG, or the M register, or the value from data. This is a 16-bit data input that goes directly to that register. I mean that multiplexer. And then based upon this value, which is the OP2 value, a 2-bit value, based upon OP2, we're going to select one of these 4 inputs to the MUX 1 and send its value on to ALU line 2, or the input 2. ALU 1 is going to get its value from this MUX, and this MUX is either going to give it the A register by default if this is 0, and that, I think that is from, let's see, maybe OP1 if I remember correctly. Let's see if I can trace that back. Yeah, that MUX 2 is selected based upon OP1. That's a 1-bit value. And if it's a 0, then A register is loaded into the N1 of the ALU. If it's a 1, then the 5-bit constant is loaded into the N1 register of the ALU. And then the opcode is loaded in the ALU, and that tells ALU what to do, whether it's an add or negate or whatever, the several things that the ALU is capable of doing. Then the output from these go to various places within the logic to fill out the logic. ALU, for example, goes to the result output. It also goes to these AND gates up here that we mentioned, where the one of the possibilities was for the ALU result to go into the MR, and the ALU also goes into this AND gate that supplies one of the possible inputs into the A register. The M register goes to the result output. It also goes to the PC input, the program counter. It also goes to the OP2 goes to the MUX1 multiplexer as a possible value to send to the ALU. And then the jump zero logic here, I think we've already explained that for telling the PC to jump to a new value based upon the input of MREG. So that's hopefully that gives a little explanation to that logic. And I know that's kind of a quick overview, but I hope you were able to get something out of it. If you have some questions about it, be sure to let me know in the comments. I'll be glad to answer any questions you have. Let's go back into the Microhard program. I'll show you what the first the first design I created on in Microhard, and this tested out all right, but I noticed as I was trying to improve it after redoing my design in digital, that there are some serious problems with this design. And I don't know why I did that, but if you notice here under the input wire up, I said to load the 14 lower bits of data input to MUX2 N4, 1 to 14. And if that works, that will work a lot of the time as long as you don't have anything up in those upper 2 bits of data. But if you ever depend upon that 15th and 16th bit within the data input, then the outcome is not going to occur. Apparently, the testing that they did for this logic did not include any data that had a higher number than what would fit within these 14 pins. So it went ahead and passed it, even though it really is not a valid design. Going over now, we go to the what I've been working on. This is what I've come up with, and it's very similar to what I did before, but I went through and tried to arrange this a little bit more, with a little more consistency. The difficulty in doing that is that you have to do it all on one screen, and trying to get all of this in one screen in a way that is easily recognizable is just almost impossible. Because you have to put multiple connections on the same line just to keep it all on one screen, and that really made it difficult. I wish the program would have given us a little more. I wish the program would have given us the ability to scroll on this, so that we could have had a little better looking designs in the wiring. But it is what it is, and I guess that's okay. When I hit Control Enter for this design, I finally got it to pass, and I had some difficulty getting it to pass because I left out connections that were just hard to see. It was hard to see if the connections were there. You know, I think the smart way to do this would be to have a list of all the components and all of their connections listed out, so that you just go down and stick all those connections in there. But I didn't do that on this, so I missed some of the connections when I was wiring this up. But once I got all the connections in there and ran the test, it gave me a verification pass. What it did not do was saved my new design, and I believe the reason for that is that it doesn't see this as a better design than the design I had before. And I'm guessing that I may have one or two NANDs more in this design than in the finished design. As a matter of fact, I think I can find out. Let's go over into the statistics and see. This one is 3022 NANDs. Let's go down to the settings and over to statistics. Come down here to the CPU. Yeah, it says that the last one I did was 3020. That's the score, and that's also the number of NAND gates. And the new version, I believe, is the same. If I go back to working design, hit Control Enter, I got 322. So I got 2 additional NANDs there, and I know how to fix that. I'll just go down here and see if I can't work that out. And what it is this AND gate is really not necessary. So I'm gonna delete the AND 6 and just send, let's see, what did I delete? Let's see. And 6, where is and 6 entered? It's up here. And 6, it's right here. Constant and 6. If I go here and just say load 1 to 5, that will give me basically the same logic as that will give me the same logic, but what I need to do is not give that to AND. Not give that to the AND gate, because I'm going to remove that. But send that to MUX 3.1. And let's see, anything else I need to do there? Let's see what that says. 1 to 5, different bus widths. All right, and come here. And I can remove it here. No, it says it's still different bus widths. Okay. I thought you only had to put it on one side, but I guess not. Verification passed. Still gave me 3022. So I don't know why it wouldn't, not sure why I still got the same number. I know why. It's because I still have a reference to that AND 6 gate. So let's get rid of that, and that ought to save me a couple of the NAND gates. Aha, 2990. That saved a few NAND gates. Click OK, and now the solution has been updated. And that gives me a working solution then in finished, where the previous one really didn't work. Well, it's been a lot of a talk about a CPU that's really not a very good CPU. It has it is a CPU. It is able to do some work, but I wouldn't want to use it if I were going to program. Well, that's going to be all for this series of videos. We appreciate everyone who has come to watch, and hope that you'll have some interest in our live videos coming up in just a couple of weeks. And be watching here. I'll have more information on the main page of my videos, and we'll look forward to seeing you there.